Today we are very, very pleased and honored to have with us Dr. Donald Glazer, a physicist who, at the age of 34, won the 1960 Nobel Prize for Physics for his 1952 invention of the bubble chamber, a type of particle detector that became the mainstay of high-energy particle physics throughout the 1960s and 1970s. Born in Cleveland, Ohio, Glazer received his Bachelor of Science in Physics and Mathematics from the Case Institute of Technology in 1946. He received his PhD in physics from the California Institute of Technology in 1949. From there, Glazer accepted a position as an instructor at the University of Michigan and was promoted to professor in 1957. He joined the faculty of UC Berkeley in 1959 as a professor of physics, and in 1964 he was given the additional title of Professor of Molecular Biology. His current position since 1989 is Professor of Physics and Neurobiology at the Graduate School. The goal of his lab is to construct computational models of human visual systems and explain their performance in terms of physiology and anatomy. After his talk, we'll have plenty of time for questions. Please wait for us to give you the microphone so everyone can hear, plus we are taping this. And please join me in welcoming Dr. Donald Glazer.
Thank you, Dan. It's a great pleasure to be here after 45 years of not doing physics. I enjoyed physics a lot, but physics was getting very expensive and very complicated, and more as the Bevatron gradually got decommissioned, required a lot of travel. And so in my lab now, where I work on computational models of the human visual system, I have lots of graduate students who describe themselves as refugees from high-energy physics. When I arrived in Berkeley, I thought I had arrived in heaven for two reasons. The first one was that an administrator came to me and said, well, we need to set up a budget for your research group. I said, okay, let's do it. How many PhDs do you want? And I said, well, me plus 3 more. And then he turned to leave. And I said, but don't you have any more questions? He said, oh no, we'll take care of all the rest of it. And they knew exactly, on some global average over the lab, how many machinists and technicians and electricians and so on would participate. No thought of writing grant proposals, nothing. It was just, those days are gone forever, as you all know, especially if you work on the campus. The other thing was the incredible quality of technical help and resources. There was a class of technicians, I don't know their official job description, but they were called ACTechs, which I guess meant accelerator technicians, and they could do anything. They improvised in emergency situations, they did planned projects, and so all you had to do was decide what you wanted to try to observe as a physicist, and the rest was just taken care of. It was a real welfare society, in the good sense. Well, I want to start describing my own contribution with a fantasy that motivated it. I had gotten my degree in cosmic ray physics working in the lab of Carl Anderson, who won the Nobel Prize for discovering the anti-electron, the positron. And that was a very big deal because not only it was a new particle, but it was the first antiparticle. So it gave experimental proof to Dirac's theory that there would be antiparticles corresponding to every so-called real particle. And so as a graduate student, my job was to babysit a large cloud chamber looking for what Carl Anderson called pothooks, and later became called V particles, because they were particles that left a V-shaped track, generally neutral particles. They seem to come from nowhere and suddenly make these V's. but we only got one a week. And so I could do all of the relativistic calculations on my slide rule, which is all that was available essentially, to figure out what was the mass and charge and what kind of particle it was. And things were going very slowly, and it wasn't much better at the accelerators because there wasn't any really high-speed image-forming detector which allowed you to find things that you didn't expect. If you knew exactly what you were looking for, a counter experiment could be defined and gather data much faster. So I developed the fantasy that if I was clever enough, I could invent a detector which was much more efficient and go to the top of a mountain where the cosmic rays are more plentiful and spend my time skiing and hanging out in a log cabin and now and then checking to make sure that the chamber or whatever it was would work. And so I did some preliminary calculations and I came up with a very unhappy answer that that dream wouldn't work because the latent image in what turned out to be the bubble chamber was very short, because a bubble chamber works as if you had plunged a hot needle into a liquid in a pressure cooker. And when you compute the time that the putative centers for bubble development remain hot enough to do something, it was 10 to the minus 8 seconds. So cloud chamber, as you know, a particle goes through, you have Geiger counters scattered around, and then you expand the chamber and you have plenty of time because the droplets don't go away. In the bubble chamber, it turned out that was impossible. So against my wishes, I had to cast my lot in with those who were using particle accelerators. And there you relied on knowing exactly when the beam would arrive so you could expand the chamber. Turns out we had to take pictures in a microsecond in order to get very sharp ones. And so I think the first slide will show that. If we can see, do I start it? Yeah, so these are the first bubble chambers. Working at Michigan, I was blessed that we had a departmental glass blower. And so he made all these things to try. And this is the one that you will see movies of. But I began with a much simpler thing even than this, because although I had made a detailed theoretical analysis of under what conditions the tiny energy loss of a minimum ionizing high-speed charged particle would deposit in a liquid, and was that enough to make a bubble? To make a bubble, you have to provide enough energy to build up the surface tension as the bubble surface grew. And so I don't know if I have a slide of what I want to show you next, so I'll just describe it. Suppose you have two of these things connect, and this is heavy wall thermometer type tubing. Suppose you have two of these connected together, so you have a U-shaped structure. And you fill this thing with some liquid, and I used diethyl ether because it had the right thermodynamic properties, and you could buy cans of it in the chemical stockroom without knowing anything about chemistry, and which I didn't. And the stuff in the can would be guaranteed to have the same parameters as you could find in the chemical rubber handbook. So I could do a calculation reliably because I could get pure diethyl ether. But it's dangerous stuff. It's very flammable, and it's the same ether that's used as an anesthetic. So imagine two of these coupled together, and this one is sitting in a bath of cold oil and filled with the liquid. Then suddenly and this one here is sitting in a hot bath, the one under here. And so suddenly I switched the baths. So suddenly this one is hot and this one is cold. And so the pressure is reduced enormously by cooling it. And this one is now hot and it wants really badly to boil. And so it's in a state called superheated. So it's thermodynamically unstable. And the question is, if I expose this to radiation from say a cobalt-60 source, which I used, then would radiation be sufficient to trigger boiling over here? Because it had enormous excess stored energy. But the problem was one of nucleation. Where does the bubble begin? And what can set it off? Well, the answer was it worked. And in fact, one of the graduate students in Ann Arbor helped me. He was 30 feet away with a cobalt-60 source, and when he pulled it out of the lead can, this thing boiled immediately. So I knew then that one could trigger boiling. And then after that, it was just a question of hardware. And so I borrowed a camera from the engineers that could take 3,000 pictures a second. And, oops. And this is a cosmic ray. There was no way of triggering this with Geiger counters, as I mentioned. And so we know now that the bubbles grow to be too large for physics within about 300 microseconds. And so the problem was we had to catch it much earlier. And of course then the thing simply explodes into boiling. And one of the virtues of this system is that you can recompress it very quickly and come back to the sensitive state. Now, I considered a lot of other detectors. I considered supercooling so that you'd get crystals formed, but no way could you imagine reversing that quickly. I even tried a funny trick with a dacron. The monomer of dacron is called, I think, acrylonitrile, and it makes a colorless solution. And I had the dream that if a particle went through a solution of acrylonitrile, it would polymerize it along the trail, and then you would get a little Christmas tree showing where all the tracks were, and all you had to do was pull that out and measure the angles. And so I tried that, and what happened was that my solution of acrylonitrile turned brown, and it didn't make any structure at all. So I had stumbled on a nice dosimeter, but nothing of any use for me. There were some other crazy schemes. Well, one of them was the spark chamber. I tried that too, and that worked pretty well, but the crude one I had didn't give sufficient precision to be useful for measurements, but other people have developed it, and now that's the main tool that's used in high-energy physics if you want an image. And so here is one of the luckier tracks I got, showing that it could be very small if you got there very quickly. More of the same. So this was the first thing that we controlled with anything other than crude thermodynamics. It was really pretty crude. Here's the chamber itself, and here's a manually run piston. This thing is a coil electromagnet that I got from a radio that my family owned in 1932, which was in my junk collection. And I drilled a hole through it and put an iron clapper in the bottom. And so I had a rubber-coated thing here that I could release very quickly by discharging a condenser. And so that was my rapid expansion gadget. Oh, I should say, at this stage, things looked pretty good. So I asked for a grant from NSF. I think I asked for $2,500. And a letter came back saying it would be an irresponsible use of public funds. Unfortunately, I can't find the letter, but that's what happened. And so the dean of the graduate school in Ann Arbor took pity on me, and he had a slush fund and gave me $2,500. But as you see, most of this was made out of junk, and the rest of it was done by a really excellent machine shop in the physics department that didn't have any recharge, so you didn't need any money to get really professional work. And then if you expose that little chamber I just showed you to a radium source, you get all these little tracks. And this is Dave Rahm, my first graduate student, looking at a chamber which was designed to work at accelerators. It's getting bigger little by little. And I built this camera. It's a stereo camera, which I guess used 70 millimeter film. And this thing here is a xenon flash tube, which was used in airplanes during the Second World War for an identification, friend or foe. And so this thing gave a coded pulse of light. And luckily, one of my colleagues in Ann Arbor had worked on this thing, so he had some spare lamps lying around, and that was the system. But with this, we could, of course, you can't make a shutter, which is a 1 microsecond device, but this thing, having a parallel arcs, could easily give you a 1 microsecond exposure. And then it gets bigger and bigger. This one, in fact, is a xenon bubble chamber. At this stage, Louis Alvarez here in Berkeley and Jack Steinberg at Columbia and many others began building big bubble chambers with magnets and all the stuff that the modern ones have. But we didn't have any accelerator projects in Ann Arbor at that time, so I couldn't build anything like that. But I chose xenon, which is an exotic substance. It's present in air in 1 part, in, as I recall, 10 to the 7. So you get it by fractional distillation of air. And so we had a cubic foot of it, which was close to $1 million worth, everything I could get in the US and Germany, and the Russians wouldn't sell theirs. And the point of it is that if you have a liquid with a very large atomic number, then it's efficient as a converter of photons, and the photons then produce electron pairs. So it's a way of seeing photons in nuclear reactions which don't show up in any other detector of this kind. Oops. And this is Louis Alvarez's chamber. He assembled a very large group here in Berkeley of engineers and physicists and built this remarkable device. The chamber worked with hydrogen, which is what all of us were interested in, because then you know that the target is only protons. And so if you see a spray of tracks coming out of a collision, you know that those particles weren't there in the target, but rather they were generated by the incoming particle. And many non-physicists don't realize that E equal mc squared doesn't only allow you to predict big bangs in nuclear bombs, but it also allows you to say, well, now I convert mass into energy and I get an explosion, but I can convert energy into mass and I get a spray of new particles. So it's an equation that works in both directions. The chamber inside here was about the size of a standard bathtub. And the reason it's so huge is partly it's a cryogenic system, very low temperature for liquid hydrogen, and it needed a powerful and large magnet. The largest chamber that was ever built was built at CERN, and it was a bathtub about 2 meters long with hydrogen. And here is a picture of what they were able to get, in which you see particles being produced by incoming collisions, many of them. And I should say that when I arrived in Berkeley, we started doing experiments with our xenon chamber, and there was a lot of leaking radiation around the lab from the Bevatron, even though it had stacks of concrete around it. And so for each experiment, ours in particular, they built a concrete shielding house. Each block of concrete was about the size of a minivan, and they stacked them up all around us with a roof overhead and so on. It was quite an impressive thing that they could do that in an hour or two with a single naked light bulb coming down inside. And in there, my students and I were sitting, babysitting the bubble chamber and the electronics to make sure everything was working. About 2 or 3 in the morning, we get a little bit loony. And so we began to be philosophical. And one question was, why are we working so hard? And the thing that worried us was that the prevailing cosmological view at that time was that there was a Big Bang, and then an expanding universe. And after a while, like an accordion, the expansion could go no further, and gravity would pull everything back together, and there'd be a big crunch. And when that crunch happened, everything would be incinerated. So why are we trying to generate all this sophisticated knowledge when it's just going to go away? And then it occurred to us if we were right, there must have been several generations of physicists before us sitting in concrete boxes just like this, and they must have worried about all that work for nothing. And so they probably were trying to invent a scheme which would allow them to leave behind some trace so the next batch of physicists would know that they were there. And so we were trying to figure out, now how could we possibly do that? And so we decided, well, in nature, at least in physics, many things are symmetric. For every particle, there's an antiparticle, and so on. So we decided that if we could do some kind of trick to introduce an asymmetry into the big crunch, for example, maybe there are more protons than there are antiprotons, then the physicists who came after would say, hey, somebody tampered with the system. And indeed, there are more protons than antiprotons. So it was fun, but it was also stressful. But we got a lot of pictures, not as good as this, because we had no magnetic field. And here's the typical thing that all of us were looking for, in which a high-energy particle comes in, hits a proton, and generates two neutral particles, which don't have very long lifetimes, and then they decay into ordinary particles. Well, that's revisiting things that happened 45 years ago. The bubble chamber became very common. Everybody was using it who had an accelerator. But since then, it's become obsolete with the advent of the colliding beam accelerators. Because in the good old days, you hit a target with a beam, and then you put your detectors around it, and you could shield them because you knew where the energy was coming from. But in a colliding beam machine, two particles coming together make a more or less isotropic spray of products, and the background is hellacious. And so a bubble chamber will be completely swamped with radiation. And so it's only the electronic detectors, wire detectors and parallel plates and all those things, that have the temporal resolution to pick out some time slice of what is happening, and thereby work in a high background. Well, so my fantasy didn't work. I couldn't go to a mountaintop and collect particles, but I was trapped because this was exactly what was needed by the accelerators. And it improved the data rate of collecting data by a factor of about 1,000, which is the density of a typical liquid compared with the density of a vapor in a cloud chamber. So the thing could be cycled fast, so we could keep up with a pulse every few seconds, and get a very high probability of seeing things in the chamber. When I was a graduate student at Caltech, Carl Anderson was looking for just exactly the kind of pictures I just showed you, but they never happened in the chamber, so the standard thing was to put a lead plate. So here's a big chamber, and here's a lead plate. Cosmic rays come in, but everything happens in the lead plate. So you don't really know, are you getting the whole story, and what is the nature of the products? Well, to improve things a little bit, he decided to use a platinum plate. So he went to the Platinum Company of America, and they said, okay, we'll loan you a plate. It's for the good of science. As I recall, this plate was about 1 centimeter thick and maybe 30 centimeters long. I hesitate to guess what it would be worth. And everything was going very well. Good experiments were resulting from it, but after a while, the Platinum Company of America said, we need our plate back. And so Caltech was required to cough up quite a lot of money, I don't know the amount, to buy this thing so that they could continue what was a 3 or 4 year program. And finally, when the program was over, they put the plate in the attic and people forgot about it. And a little while later, somebody discovered it and said, hey, what is this? And so platinum is a commodity. So they went to the Platinum Company of America and said, hey, we want to sell you the plate. And Caltech made a huge profit. One of the few cases in which research literally pays off. Well, I don't think I have any more stories to tell you. When we first arrived here, we came in an enormous one of these 40-foot trailers loaded with bubble chamber junk and playpens and all kinds of stuff belonging to the research group. And that trailer stayed parked somewhere on the hill for, I think, 20 years before somebody asked, hey, what is that and whose is it? And so finally I signed off on it, and I don't know what happened to it. I presume it was sold. Well, you all have a choice. You can ask me questions, or I can give the second lecture. Let me just tell you one of the more interesting things that we are doing now in neurobiology of vision. There is an oil painting by a French artist, Issa Levian, in 1985, which looks like a wagon wheel out of a Western movie, but the rim is painted in a bright orange color, and there are many, many thin black spokes, maybe 50 or 100. When you look at this painting, you see water running around in the rim. Nearly everybody sees that. And so what is happening in the brain that you misinterpret so grossly an oil painting? And I speculated that, well, maybe there's noise in the brain because the neurons work by sending out trains of voltage spikes, which are maybe 70 millivolts high and 1 millisecond wide, and those are more or less random. The average spike rate will tell you how bright a light is or how hard somebody is pressing on your hand. So the spike rate gives you information, and this is the language of communication within the brain. And so in such an environment, there must be large fluctuations, as there are, and maybe that noise was causing this effect. One night, we had a dinner party and showed this picture to our guests, and everybody saw it and oohed and ahed, and that was lovely. And then after dinner, one of the men wandered over and looked at it again. He said, I can't see it anymore. And so luckily, this guy said, you know, I've had 3 glasses of red wine for dinner. And it turns out he is one of the world's experts on alcoholism. And in fact was the founder and director of the Gallo Institute for the study of alcoholism. So then we did a bunch of experiments, and sure enough, it's true. But then we decided we had to do something a little more scientific, so we built a thing called a racetrack, which is an annulus, and we sprinkle dots inside of it at random. We make 1,000 of these random patterns, and then we show the thing as a movie. And so what you see is little dots dancing around, but what you also see is the dots go swarming in this direction, or they go swarming in the other direction. And so there we were deliberately introducing visual noise, randomness, and generated the same percept that this oil painting generated. But then the main reason I'm telling you this story is that the next thing that happened is that I said to myself, I want it to reverse, and it did. So I didn't say it out loud. So the act of thinking that you want this illusory motion to go the other way affected your perception. And so the next step was sort of, fooling around, touch the desk, so on. Turns out, bite your tongue, reverses. Press your big toe down in your shoe, it reverses. So the conclusion is that almost any neuromuscular act, whether mental or actually physical, could change your percept of this unstable configuration. And so we thought, well, okay, if you're sitting in the jungle and it's quiet and somebody taps your shoulder, you better pay attention. So it has enormous survival value to be alert to any change in the perceptual environment. And so then I began to wonder, well, maybe I don't have to do anything. Maybe a passive signal will do it. So I invited my wife to come to my studio, and she was watching the thing, and I tapped her on the shoulder when she couldn't see that it was coming, and it reversed. And then I blew in her ear, and that reversed. I used a baby syringe, one of these rubber things. So it turns out that either touch or sound, I clicked a couple metal things together, or flashing a light in the background, could alter a visual percept. And now you know everything I know. That's where we are. We have a very surprising phenomenon. We have lots of data. In fact, we even tested it with marijuana. Now, I wouldn't dare do that on the campus, as you could imagine. But I have a friend who is an oncologist at UCSF who is studying the use of marijuana for controlling pain in the cancer patients and AIDS patients. And so for every 2-hour interview, he allowed us to give the patients this visual test, when they were stoned and when they weren't. But I was not allowed to be there. We had to teach the nurses how to run the experiment because none of us, students, nobody was allowed to come and see and meet and talk with the patients. Bottom line, it had a big effect. When they were stoned, they really were much less responsive to this kind of thing. Many curves, data, and so on. And so that's where we are. It looks as though chemical influences like alcohol and marijuana, which one thinks of as somehow calming influences, in moderate doses anyway, seem to reduce what we think of as the effects of noise. And so it's a very exciting development, and we're trying hard to think of how are we going to nail it down to a particular function in the brain by doing more of these so-called psychophysical experiments. Anyway, I thank you very much. I'd be very happy to answer questions.
We have time for questions. Raise your hand and we'll get you the microphone.
Dr. Glaser, a number of us have heard stories over the years about where the idea of the bubble chamber came from a glass of beer in Ann Arbor or what. Could you share with us sort of the truth?
And nothing but the truth. Yeah, well, I was working on the bubble chamber. Oh, and there's another story I can tell you related to that. I forgot. Fermi invited me to come and give a talk in Chicago. And I was, of course, greatly honored. I was a very young guy. And so I gave my talk. And afterwards, there were a lot of questions. And he kept asking me, why did you think it would work? And so I spelled out, there was a lot of fancy thermodynamics and statistical mechanics and so on, having to do with superheated liquids. And he was very polite and friendly, but he kept insisting about details of the theory. And afterwards, I asked another young physicist who was more my size, why did Fermi care? Well, Fermi also thought of the same idea, but he proved it couldn't work. And then later, I was shown a book on thermodynamics that he had wrote. I think actually his students wrote it, but it was from his lectures. And there was a diagram in there having to do with determining the vapor pressure over a curved surface. And you know, the standard capillary tube experiment, you have a glass tube and you stick it in water or mercury, and then the liquid forms a meniscus, and the surface tension then pulls the column of liquid up. And he had such a diagram, but it was wrong. They had forgotten a very small thing. So I was just lucky that I didn't know about his book on thermodynamics, or I would have proved it was wrong also. But coming back to your question, I was working on this, and in Ann Arbor, in those days being the late, the early 50s, there were no summer salaries. And so people came to Ann Arbor, physicists, for conferences for the sheer joy of it. And they stayed in fraternity houses, and they included Freeman Dyson and Bruno Rossi and a number of other very well-known physicists. And after our evening session, we would go to the local beer place, which was called the Pretzel Bell, which was a beer place that was usually used for celebrating football victories, and a big pitcher of beer and in the table. And I took a lot of ribbing. They knew what I was doing, but they said, look, Don, it should be trivial. You can see streamers anywhere. Why is it so hard for you to do that with your gadgets? So that's the real beer story. And there are various versions of it, but that's what really happened.
Don, I seem to remember Mel Ruderman in his graduate level thermodynamics course around 1956 tried to describe how bubbles form in liquid hydrogen, and the theory then, as he explained it, this is a thermodynamics course, was that the surface tension would have to be balanced by electrostatic repulsion. That didn't work very well, and I think Seitz came along, Frederick Seitz, and managed to explain things. Could you elaborate?
Yeah, I tried that also, and the reason for trying it is very simple. That's how cloud chambers do work. So a droplet in a cloud chamber grows if it's charged, but not otherwise. So there are conditions of supersaturation of the vapor that allow growth only if the bubble is charged, and that's how you get tracks in cloud chambers. So it was natural for us to try the same trick, and it didn't work. So I ended up by using another model, which was that there was energy deposited, and that energy increased the local vapor pressure. Now, when I began to work on bubble chambers, I couldn't find any liquid that had a small enough surface tension that the little bit of energy deposited by a fast particle would make any difference. And so that's why I had to make the liquid superheated, because of course as you go hotter and hotter, you get to the triple point or the critical point, and then the vapor pressure continues to, it disappears at the critical point. The liquid and the vapor are identical. So in order for the bubble chamber to work, the liquid has to be, I forget the rule of thumb, about 2/3 of the way from the boiling point to the critical point. And so in diethyl ether that I was using, the boiling temperature, as I recall, was around 36 centigrade. And my theory predicted that you had to get to, I think it was 140 degrees centigrade. And so it's an insane idea that you could get something that boils at 36 up to 140 without it exploding and boiling. And so that was why I had to do that primitive little experiment with the two bubble chambers joined by a connector to see whether it was really possible. And that established that it was possible, but I thought only because everything was clean. So you know that chemists very often put ground glass in the bottom of their test tubes so that the boiling is regular. Instead of it gets hotter and hotter and then blurp, and the liquid comes shooting out of the test tube sometimes. So it's known that in order to get easy bubble formation without superheating, as the chemists experienced it, you have to provide something that nucleates, and ground glass with sharp edges or scratches in the glass can do that. It turns out that if you take the picture very quickly, boiling does begin all around the edges where the gaskets are. But you get there in a microsecond, and you get your tracks, and then the boiling takes over. So that was an essential part of the theory, that you had to go very far above the boiling temperature. And the question whether you could have a liquid that would remain stable for a second or two, that it requires you to take your picture. Anyway, that's the story.
Is your rotating dots experiment on your computer or on a website, or is it not visualizable that way?
It's on the computer, and it is on the website, but I forget the title of the website. But anyway, probably if you just Google me, you'll find a website. If not, email me, and I'll send it to you. My email is glazerda@berkeley.edu.
So have you tried these visual phenomenon experiments on people that were under the influence of other drugs that are more associated with visual phenomena, such as mescaline, psilocybin, etc.?
We're talking about that. There are two problems. One is legal. And so we have to find somebody in a place that has a legal license or permission. But the other one is scientific, and it's trickier, and that is that alcohol and marijuana and the other drugs that I've thought about act at many different sites in the brain. And so the question is, how much do you learn unless you have some kind of focused thing to say it's here or it's there or some other place? So I'm not pursuing that very hard, because I'm sure we could accumulate a lot of data, but I don't see any way to get a useful interpretation, except general reduction in arousal or spike rate, whatever it is. But we are beginning an experiment with earphones to introduce noise acoustically, and we're trying other modalities too. We have an experiment planned to see whether smell, if you introduce a new odor suddenly, will that work? But the chemical route, I think, is... But what we are doing is really exciting, and that is we have a collaboration with a group in Minnesota that have an MEG setup, magnetoencephalogram. And this thing is a huge football helmet, which has, I think, 284 squids in it, which are exquisite measures of very, very small magnetic fields. And those things are known to detect mental activity. And so we're hoping that they will use our software for the racetrack and all that. And we're hoping that they will be able to localize where in the brain, with these 284 things triangulating, the activity is focused. So that's a very sophisticated and difficult experiment, but I think it's more promising.
With regard to the beer experiments, we did, you may probably be aware of this, what was probably the most sensitive beer experiment by putting a glass of beer in a uranium beam at the Bevilac. With the, this is Frank Crawford that did this, and so it was probably the highest density of ionization you could get for a track. And so this glass of beer was placed on top of the radiotherapy table, and cameras were set there to look at it, and no tracks were seen. However, the experimenters had a good time in consuming the apparatus when it was over.
Well, I considered obviously using beer and soda water and so on, but water has a very high surface tension and a very high critical pressure. So I decided that water would be really an awkward substance to use, because the experiment required extremely sturdy equipment. So I tried it. Oh, I forgot, there's another beer story, which is that I had all this theory, and I predicted, as I just said, that water would be a lousy choice. But just to be sure, I imported a case of wine into my lab, a beer into my lab, and late at night, 2 in the morning, whatever it was, I put it in a hot water bath, or maybe it was oil, And I got the beer very hot. And then I pulled the cap off to see how high it would shoot. And the answer was it hit the ceiling. And then I did the same thing with a cold beer, which foamed a little bit, as you know. And the bad news is that the chairman of the physics department was a very strict teetotaler. And he arrived in the morning and the whole building stank of beer. But I wanted to make sure I wasn't overlooking something and that my theory wasn't grossly wrong and so on. And so that was almost the end of my career. Well, I think Frank's idea was right, that uranium would be, it goes as Z squared, and that would be a good choice. But the real trick is to get the temperature high. That's the only way to reduce the required surface tension.
With this visual effect, can you get does the effect reverse through cognitive changes if people are sort of primed with different ideas and then the line of ideas changes? Does it switch direction?
It's a cute idea. We haven't tried it. Without any interference at all, just looking at it spontaneously, it reverses spontaneously, and we don't know what the reason is, but presumably the fluctuations. I should say that if you show, as we did, 1,000 frames, and I guess it was 30 milliseconds per frame, something like, then if there's a dot here in one frame, and if there's by chance another one here in the next frame, you get AB. And that is the so-called two-dot motion stimulus. And that's what you see when you see a theater marquee. The lights seem to be going around, but they aren't. They're just going on and off. And so that's a well-known fundamental part of perception of motion. And so our explanation for why you see motion at all is that there are chance coincidences like that at a certain rate. And to test that, we've added deliberately some of those AB pairs. So if you start with none of them, you see switches. If you put in 10%, then it has a preference. And for large audiences, I can ask people, okay, can you reverse it? Well, if I put in 10% bias, everybody can still reverse it. 20%, a lot of people drop out because the bias is too strong. Nobody can do 50%. And in between, there are a few people who claim they can do 30 or 40. So you can measure the strength of the phenomenon, as we have done, in that way. But it's an interesting thought to try to offer some suggestion or some description of a scene, or that's, I guess, what you have in mind.
Right.
It's a nice idea.
Don, there is this phenomenon, if you look at the drawing of a cube, that it can reverse.
Right.
Is that a similar thing?
Yeah, that's the so-called Necker cube. Sorry?
Can it be used for these experiments?
No, it can't. And the reason is this, that there are a lot of such so-called bistable objects in vision. Another one is the vase and face thing. You see a shape like this, and you can either think that you're looking at a vase or two faces. You've probably seen that one too. So there's a whole library of those things. But the characteristics of them is that it takes a second or two or three or four from the time you say to yourself, I want it to switch, until it happens. But this one happens immediately. By that I mean a tenth of a second. And so it's unique. And so the mechanism is different. And I can't tell you what the mechanism is, but that's our task.
I have a question about perception of musical pitch. This can change even for people who have very, very good relative pitch or perfect pitch. As one ages, one tends to hear things higher than they really are, I believe. Do you know what would explain this? Have you any interest in pursuing it as a one-time viola player?
Yeah, Jan, that's a good question. No, I mean, I've heard the same things you have, but I don't know very much at all about hearing. But we're starting to work on it, so maybe in a couple of years I'll know a little more. Work on it in a sense of trying to introduce noise, thinking that by introducing various kinds of sounds, beeps and burps, but also just static, that we can affect what I'm thinking of as the level of arousal, which I think means the spike rate in the brain. And so we'll have to learn about such things. So far, the things that we have observed in the lab that I described are not very age sensitive, unless a person has a known defect. But for the age itself, if everything else seems normal, it doesn't seem to play a big role. That's vision only.
You're talking, all these things we're talking about, perception experiments. What's the role of noise in abstract thought? If I'm trying to solve a physics problem, can you see what effect noise has, and can you use, for example, alcohol to suppress it, or and make my thoughts better?
Actually, the most exciting thing that we're working on now has to do with noise and with a phenomenon called stochastic resonance, which is well known to engineers and mathematicians. And it's the idea, I guess I'll just do some hand waving. Suppose you're looking at a light bulb, which is very dim, so you really can't see it, but you're told there's a light bulb there. And suppose that the brightness of the bulb is going up and down because somebody is adjusting a resistor or something. So here's this signal that you can't see, which is below threshold. Now suppose you add to it random noise. So now the signal is whatever this is, plus the random spikes. Now if a spike happens to appear at the same time that a crest appears, the sum of the two can rise above threshold. That's called stochastic resonance. And I think it's a bad term. We're calling it in our paper stochastic sampling, because the noise signal is taking samples of an otherwise imperceptible input. And there is pretty good evidence that and that improves performance. That is, in engineering systems, when the signals are too low to be detected by whatever the hardware is, this will give you at least a sample of them. And you have to connect the dots with some kind of smoothing algorithm, but at least you have some information. And so that's a growing field of research. And the question we're wondering about is, does stochastic sampling help our vision? And so we're doing experiments to see, and there are some experiments. We have a picture of Big Ben in London, which has lots of junk on it, so you really can't see it. Now, if you add noise at the right level, you can see it. So it already is known that introducing noise improves vision at least. Of course, too much and you get killed by the signal-to-noise ratio. Too little, there's no effect. So there is a range of introduced noise that improves performance, including human vision. However, my own belief is that when you walk into a new site, you're going to the beach, that your brain does some kind of a quick survey and forms a context, which is different from walking into this room, which is a very complicated image. And I have a context for this too. And that maybe the visual system is smart enough to adjust the level and maybe even the statistics of the noise signal to optimize vision in the current environment. I have no proof for that at all. But it seems to be crazy to have a system which doesn't know what's going on, because only if you do can you do the best job of data processing. Anyway, that's what we're most interested in now, and beginning to do a lot of experiments.
One more question. I know that in the visual system that there's a certain background firing rate. Is that one of the possible sources of at least some of the noise? Is the dot effect, is it perhaps affected by something like dark adaptation that would affect the background firing rate?
Well, the whole brain has random spiking of neurons all the time. And my thought is, and I think there's probably evidence, that when you're excited or aroused by any stimulus, that the rate goes up. And I should say that physicists have a very definite definition of noise. Namely, if you have a resistor, you can compute the noise, the electrical signals as a function of temperature. And that's a classical calculation. The engineers have to have a definition of noise, which is also fairly well defined and governs the design of engineered systems. In biology, it's kind of weird. We don't know everything that goes on in the brain, obviously. And so if I shine a light, then presumably increased spiking occurs in the visual system somewhere, and you can pick that up. That's pretty well known. But the background keeps going. And so biologists are in the habit of calling noise any signals that I didn't cause, which is not so foolish because it's so complicated that we can't really compute anything. And so in an experiment, you give certain stimuli and you want to measure the response. Even with the MEG setup, you have to do that. But all the time there's this other stuff going on, which presumably is not raindrops, but it's things happening elsewhere in the brain that you cannot control or monitor. And so in general, that's what noise is called. And the game, of course, is to try to untangle that, to understand as large a fraction of the signals as you can.
And if there are no more questions, thanks again to Dr. Glazer for that excellent